What if we could dial down the sun, not permanently, just enough to buy the planet some time while we figure out the rest of the climate problem? That's the idea behind geoengineering, and it sounds almost absurdly simple until you start pulling it apart. The basic concept has been floating around in scientific circles for decades, but in the last few years it's moved from the fringe into serious research programs, government discussions, and some very real engineering questions. So let's actually dig into how it works, why it's so hard, and why some of the smartest atmospheric scientists in the world are both intrigued and genuinely nervous. The version getting the most attention right now is called stratospheric aerosol injection. The idea is to spray tiny reflective particles, usually sulfur dioxide, high into the stratosphere. We're talking about altitudes well above where commercial planes fly. Up there, those particles spread out and act like a very thin planet-wide sunshade. They reflect a small percentage of incoming sunlight back into space before it ever reaches the surface. We actually know this works. When a big volcano erupts and blasts sulfur into the stratosphere, global temperatures dip slightly for a year or two afterward. Mount Pinatubo did it in 1991. Temperatures dropped by about half a degree Celsius globally. That natural experiment is basically the proof of concept that geoengineering researchers keep pointing to. So if nature can do it accidentally, the thinking goes, maybe we can do it deliberately and carefully. But here's where it gets complicated. First, the delivery problem. To get enough material up to stratospheric altitudes on a continuous basis, you need aircraft that can fly much higher than anything in the commercial fleet. Researchers have been sketching out purpose-built high-altitude planes with enormous wingspans and relatively small fuselages. Ungainly-looking things. They'd need to make thousands of flights per year, every year indefinitely. Because the moment you stop, the particles settle out within a year or two and the warming snaps back, potentially faster than ecosystems can adapt. That rebound effect is one of the more unsettling parts of this whole idea. Second, the atmospheric science is genuinely messy. The stratosphere isn't a simple mixing bowl. Particles don't spread evenly. Wind patterns, seasonal changes, and interactions with existing chemistry all affect how your aerosols behave. Sulfur dioxide up there also accelerates the breakdown of ozone, not catastrophically, based on current models, but it's a real effect that needs to be understood much better before anyone starts scaling this up. And then there's the regional problem. Global average temperature is a useful number, but it masks enormous variation. What cools one region might shift rainfall patterns somewhere else. The monsoon systems that hundreds of millions of people depend on for food and water are sensitive to the kind of radiative forcing changes that geoengineering would introduce. Models suggest the effects wouldn't be uniform. Some regions might actually get drier. That's not a hypothetical concern. It's one of the central scientific uncertainties researchers are trying to resolve right now. So what does actual research look like at this stage? A lot of it is modeling, running climate simulations, stress testing assumptions, trying to understand how aerosols behave under different scenarios. There have also been proposals for small outdoor experiments, releasing tiny amounts of material to study dispersion and chemistry. Some of those proposals have been blocked by public opposition and regulatory uncertainty, which itself tells you something about how politically charged this territory already is. That political dimension might actually be harder than the physics. Geoengineering the atmosphere doesn't respect national borders. If one country, or even a coalition of countries, decides to start injecting aerosols, the effects land on everyone. There's no global governance structure for this. There's no treaty. There's not even a clear agreement on who gets to decide whether research crosses a line into deployment. Some researchers worry that the mere existence of a workable geoengineering option could reduce pressure to cut emissions, a phenomenon sometimes called moral hazard. If there's a panic button, the logic goes, people might be slower to fix the underlying problem. Others push back on that. They argue that the climate situation is serious enough that we need to understand every option available, even the uncomfortable ones. Refusing to study something doesn't make the problem go away. And if temperatures keep climbing, the pressure to try something fast and poorly understood will only grow. Better to do the research carefully now than scramble later. There are other approaches in the geoengineering toolkit too. Marine cloud brightening tries to make low-level ocean clouds more reflective by spraying sea salt into them. It operates at much lower altitudes and is easier to stop. Some researchers see it as a more reversible, more testable option. Then there's space-based concepts, giant reflectors or sunshades positioned between Earth and the Sun. Fascinating on paper, completely impractical at any near-term scale, given what it would cost to launch that much material into space. What all of these approaches share is that they treat the symptom rather than the cause. They don't remove carbon dioxide from the atmosphere. They don't stop ocean acidification. They're a way to manage temperature while the real work of decarbonization happens, or at least that's the optimistic framing. The pessimistic framing is that they become a substitute for that work, and we end up in a world permanently dependent on continuous aerosol injection with no exit ramp. The researchers who take this seriously tend to be pretty clear-eyed about that tension. They're not evangelists for geoengineering. Most of them will tell you the first priority has to be cutting emissions, but they're also looking at the trajectory of global temperatures and thinking, we need to understand this option, even if we hope we never have to use it. The science is real. The engineering challenges are enormous. The governance problem might be the hardest of all. And the window for doing this research carefully, rather than desperately, is not unlimited. That's what makes this one of the more genuinely difficult conversations happening in science right now. Not because the idea is crazy, but because it might actually be possible, and that changes everything about how seriously we have to take the risks.